Welcome to the world of composite functions. Imagine a sequence where the output of one mathematical process becomes the raw material for the next. This chain reaction is what we call function composition, denoted as g of f of x. In the real world, we often need to link multiple variables. By composing functions, we can skip the middle step and create a direct mathematical relationship between our initial input and our final desired result. Notation is key. The small circle means composed with. Remember, the function closest to the variable x is the inner function, which is evaluated first. Changing the order of composition usually changes the final result entirely. Think of it as a journey across sets. Function f maps an element from set A to set B. Then, function g picks up that element in set B and carries it over to set C. The composite function is the total trip. Not every input is allowed. For a composite function to work, the value x must be in the domain of the inner function, and the resulting value, f of x, must be in the domain of the outer function. To find the domain of a composite function, we look for the intersection of constraints. We must exclude any x values that make the first function undefined, and any x values that produce an output that the second function cannot handle. Algebraically, we replace every instance of the variable in the outer function with the entire expression of the inner function. Here, we see how the linear function x plus 2 is squared by the outer function g. Let's look at a square root example. Since we cannot take the square root of a negative number, the output of our inner function, x minus 5, must be greater than or equal to 0. This restricts our domain to x values 5 or greater. In rational functions, we must avoid division by 0. Since the inner function is 1 over x, x cannot be 0. Even though the outer function g can take any input, the initial restriction from f remains in the composite. Sometimes the outer function creates new restrictions. Here, the outer function g is undefined when its input is 4. Since our input is x squared, we must ensure x squared does not equal 4, meaning x cannot be 2 or negative 2. Geometrically, composition is a transformation. We take the vertical height of the first graph and use it as the horizontal position for the second. This can shift, stretch, or reflect the original parent function in unique ways. Using a table of values is a great way to verify your work. By tracking a single input through both stages, you can confirm that your algebraic composite formula yields the correct final output. Often in calculus, you need to decompose a function. Look for the inside operation. In sine of x squared, the squaring happens first, making it the inner function, while the sine operation is the outer layer. To master domain constraints, follow this checklist. Always start with the inner function's limitations, then ensure the values coming out of the first step are legally allowed to enter the second step of the process. To summarize, the order of composition is critical, substitution is the algebraic tool we use, and the domain is determined by the most restrictive path through both functions. Keep these rules in mind to avoid common errors. Test your knowledge. If we compose f of g of x, where f is the square root and g is x minus 1, what is the domain? Think about what must happen to the input before it reaches the square root. The correct answer is B. Since x minus 1 is inside the square root, it must be non-negative. Solving the inequality x minus 1 greater than or equal to 0 gives us x greater than or equal to 1. Thank you for learning with us. Generated by Vision Solve AI.